Okay, so we're going to repeat the previous question but using a different technique. This is loop law. I actually prefer loop law over the other one. Both good. Sometimes one is easier than the other, but I just prefer this one. Okay, so let's just redraw. I'm going to scroll down here. I'm going to redraw that circuit first of all. So we had a battery, a resistor, a battery, and we had a resistor, there we go. And so what was the values again? 3, okay. So we have 3 volts, 1.5 volts, 150 ohms, 100, 150, and 200. Okay, so there's our circuit. Hopefully you need it on your page. So what we're going to do is use what's called the loop law. So when doing this one, we have to just create 2 loops, and we know that. And we're going to create an equation to represent each loop. So I'm going to be choosing this loop, 1 and 2. Now I just like to make my loops go clockwise. It's a bit easier. And it's a little more consistent, but there's different ways you can do it counterclockwise. This might get a little confusing. There's also a third loop. Some of you may see it, some may not, but it goes all the way around. There's our third loop. I'm not going to use that one, but what you can always do is you can always use that one as like a way of checking your work. It works for the third loop. We know it's good to go. So before I start, I defined current as traveling in these directions. And we saw in the last question that they all came up positive, so that means that my guess was correct. But we're just going to show that solving in this direction, it's going to work as well. So we have I1. So I1, this was I2, and this is I3. Again. And because of that, it's drawn these plus minus. So battery is always plus minus like so. But then for the plus minus for resistors, it's always opposed. We're always losing based on the direction of the current. So I'm going to have a plus minus like that, plus minus like that, plus minus, and plus minus. Yeah, it's getting a little messy, but hopefully your ear is a bit bigger. Okay, so let's create some equations. So first of all, just like last time, we're going to start with I1 must equal to I2 plus I3 based on how I define my current. Now if I look at loop 1, we're going to create an equation. So I like to start with like one of the positive voltages. So you say, okay, we have 3 volts. And we know V equals IR. So we're following voltage now. So I know I gain 3 volts here, but at this 150, the amount of voltage lost is going to be 150 multiplied by I1. It's going to be minus 150 I1. And then following this path around, loop 1 is looking at this left loop. Then we're going to pass that 100 ohm resistor as well. So minus 100 I2 because it's the current 2 is passing through. And then we pass by that 1.5 volts. So 1.5 volts. And that must all sum to 0. So there's my first equation. I can simplify it a bit too. So we have 150 I1 plus 100 I2 is equal to 1.5. Now for loop 2, we have I'm going to start with the 1.5, so 1.5 volts. This next one's where it gets a little tricky. This is where the plus minuses are very important. So notice that 1.5, if I follow this one, notice how at the 100 ohm, it's the negative sign, so on the bottom, the positive sign. So the 1.5, we're going up this one, so we're going from negative to positive, we're gaining potential. But also, according to the second loop, we're also gaining potential as well. So it's actually going to be plus 100 I2. Again, it's basically a double negative scenario. My current is going down based on my definition, but my loop is going against it. So instead, we know use the resistors to take away current, but our loop is pointing in the opposite direction of current, so we're going to actually mathematically write it as a gaining potential there. Keep following it along, or then passing that 150, so we have minus 150 I3 and minus 200 I3. That must equal to 0 as well. So we can write out, it's going to simplify, it's going to minus 100 I2 plus 350 I3, and that's equal to 1.5. So now we have three equations, and different ways you can approach this. You can use this. It's basically this math. It's math 10 now. We have three equations, 1, 2, 3. Now we're just going to do some type of either substitution or elimination to solve for our values. So we look at loop 1. I could simplify that if I wanted to. We get I1 is equal to 0.01 minus, so basically all I'm doing is isolating I1. So 1.5 divided by 150, 0.01. And that's minus 0.666 repeating, let's write 7I2. So there's our loop 1. If I look at loop 2, we get I3, so this is loop 2. I3 is equal to 0.004286 plus 0.2857I2. Now if I plug those two equations into my first equation right here, I'll get a single expression in terms of I2. So I have 0.01 minus 0.6667 I2 is equal to I2 plus 0.004286 plus 0.28. And don't worry about sig figs for this topic. So far we get I2 is equal to 0.0029 amps. And therefore, yeah, if we just take that I2 and we can solve for I1, right? Plug that value into I2, we get values of I1 is equal to 0.0080 amps, I2 is equal to 0.0029 amps, and I3 is equal to 0.0051 amps. So the exact same values we got using nodal analysis. Again, this is just an alternate method of solving.